In this video, I'm going to be describing the mean value theorem and practicing using some applications. Let's start with the definition. The mean value theorem states that if a function is continuous on a closed interval between a and b, and it's differentiable on an open interval between those same values a and b, then there must exist some input number c such that it's in between our endpoints on the interval, where the following is true: that the derivative of the function is equal to the average slope. There's a lot of ways we could say that. We could say that the instantaneous slope is equal to the average slope, or the slope of the tangent line is equal to the slope of the secant line, or that the tangent line is somewhere parallel to the secant line. There's lots of different ways we can talk about this equation. But the idea is that on a function in between a specific interval, there has to be some point where the average slope is equal to the instantaneous slope. So here's an animation where we can visualize that. The green line is representing the secant line intersecting this graph at two or more points. So this is talking about the average slope in between on this interval. This blue line is tracing the instantaneous slope as it goes along this function. So it's changing at every input. And there are actually a couple of points where this blue tangent line is going to be parallel to the secant line, meaning that the slope, the instantaneous slope, is going to be equal to the average slope. So let's watch it go through its cycle one more time. At about right there, and at about right there. So two spots in this instance or example where the tangent line is parallel to the secant line, meaning that the instantaneous slope is the same as the average slope. So the mean value theorem guarantees that this happens at least once. In this example, we can see it happening twice, so it can happen more than once. But the mean value theorem guarantees that it happens at least once. It's just talking about single locations where this happens. It's not describing an entire interval, although that may be true for a limited amount of functions. For most functions, it will not be an entire interval where this happens. It's just a single point right there, and maybe more than once, like right there. So let's talk about some applications or some practice problems. Given the function f is x squared, in between two numbers or on this interval, -3 to 5, at what value, what input does the mean value theorem hold true? So at what input value does the instantaneous slope equal the average slope? Or where does the derivative of the function equal the average slope in between these two endpoints? So we could find the derivative of our function. The derivative of x squared is 2x, or we're going to talk about c as our input variable, just a random input. And we're going to find the average slope given these two inputs. So first I need to evaluate my function given these endpoints. -3 is going to be our a. If I evaluate that in my function, I get -3 squared, which is 9. And then I'm going to evaluate my function at 5. That's my b value, so f of b would represent 5 being plugged into our function. 5 squared is 25. So on top, f of b is 25, f of a is 9, so we got 25 minus 9. On the bottom, we're just subtracting these endpoints. B was 5, a was -3, so 5 minus -3 will give us 8. So now we just have to solve this equation. This will give us the input where the derivative is equal to the average slope. So I could evaluate 25 minus 9, that's 16, and then do the quotient 16 divided by 8, which is 2, and then solve for c by dividing both sides by 2, and we find that that input is at 1. So let's talk about what that means. For our function f, which is x squared, on the interval between -3 and 5, The instantaneous rate of change, or slope of the tangent line, is equal to the average rate of change, or slope of the secant line, when x is 1. And then I can give you a little visual here. So the red graph is x squared, that's our function. At x equals 1, I have this slope. That would be the slope of the tangent line. And then I used my coordinates -3, 9, and 5, 25 as 2 points on my secant line. So the slope of that secant line is equal to the slope of the tangent line when x was 1. And we can see that the secant line is now parallel to the tangent line. That only happens on this function in between that interval from -3 to 5 when x is 1. It may happen again outside of that interval, but on that interval it's only happening once. We can also use the mean value theorem to approximate an instantaneous slope. So here we're given a table of values of some function. We don't know what the function is, we just know what the inputs and outputs are. We're going to use the mean value theorem to estimate the derivative evaluated at 7, or in other words, the instantaneous slope evaluated at 7. Well, we can use the mean value theorem to estimate, meaning we can find an average. So I'm going to use the endpoints that surround 7 or are closest to 7 on my data table. I'm going to use 5 and 8 as my interval. And I can set up my mean value theorem to approximate the slope. So I'm just evaluating the average slope side of it and saying that that's going to be approximately what the slope is at 7. So if I plug, or if I say that A is 5 and B is 8, then I'm evaluating f of 8 minus f of 5 divided by 8 minus 5. F of 8 we're told is 3. F of 5 we're told is -2. So 3 minus -2 is 5. 8 minus 5 on the bottom is 3. So our average slope is 5/3, and that's used to approximate the instantaneous slope at 7. So it's not exactly what it would be. We're just using it to approximate or estimate the slope. So we're using an average slope as an estimation.